Hi, in this video I will show you how I made my DIY Lighthouse base station. This video is mainly about the base stations, but a little background on the complete tracking system will help with understanding. Lighthouse is a laser-based tracking system. The base stations serve as the reference for the headset and the controller tracking. Each base station sweeps two perpendicular laser planes across the room and broadcasts synchronization signals and device information through infrared light pulses. The core idea behind this system is to use precise timing of the laser sweeps to calculate angles. The photosensors on the headset and the controllers pick up these laser sweeps from the base station, then the position and orientation of each object can be calculated with some algorithms. It's just a quick overview. I came across many open source projects and detailed explanations during this project. You can find links to them in the video description. This project started with a broken base station, so one day I found that one of my base stations no longer works. After some quick search, I found that one of the two lasers was dead, and there is no easy way to find a replacement. So I bought another broken base station, hoping to salvage at least one laser from it. I got lucky that one laser was indeed intact, and my repair attempt was successful. Generally, trying to repair a broken base station is not a good idea. Safety concerns aside, it will mess up the calibration and cause the accuracy to degrade. I did it anyway, and the result was not bad. After that, I was left with this very broken base station. I noticed the rest of this base station was fully functional, so I thought, why not try to repair it just for some fun? I did a lot more searches and found that it is possible to drill out the laser diode from its assembly and replace it with an optical disk drive laser. But in practice, it didn't work. The power rating of a typical optical disk drive laser is only 5 to 10 milliwatts. The base station lasers work at 30 milliwatts. Also, their current rating is much lower than what the base station lasers use, so I had to look for something else, which was quite a pain. The datasheet of a laser diode is usually unavailable. The vendors I found most of the time only provide an output power rating and occasionally with a rough current range. Since the driving current is set by the base station hardware, if the current rating is too low, the laser diodes will either get damaged instantly or have a very short lifetime. If the threshold current is too high, the laser diodes won't output enough power. I tested a bunch of different laser diodes and eventually chose to use an 830nm 30 mW laser diode with a rated operating current of about 70 mA. After I got the lasers working, I built an infrared LED array for the optical sync. In the end, I got everything working. The lasers were slightly out of focus and not aligned very well, so the tracking was a bit shaky, but it worked. After that, just out of curiosity, I wanted to try if it's possible to emulate a base station by using the LED array I built. Because all the device information about the base station is broadcasted through the light pulses, if I broadcast the same information with the LED array, SteamVR should recognize it. Once again I searched around, I found that the optical transmission protocol has already been documented. Also, there are open source trackers using lighthouses. So I built some sensors and wrote scripts to read the signals from the base station. After I decoded the information, I used the LED array to send it to a tracked object, which in my case was a web tracker. With some trial and error, it eventually worked. A base station icon showed up in SteamVR. I got very excited. I saw the possibility of making a DIY base station and decided to give it a try. So, what do we need to build a minimally functional base station? Based on its working principle, we need something to create two laser planes that sweep at a constant angular velocity and some infrared LEDs to broadcast the synchronization signal. Here is a picture of an early base station prototype from Valve. As you can see in this picture, mainly there are two motors, two lasers, some infrared LEDs, some optical components, and some electronics. To create a sweeping laser plane, the laser beam generated by the laser diode first hits a mirror that sits on the rotor, then goes through a fan lens to turn into a plane. When the motor rotates, the laser plane sweeps as well. The rotor assembly looks like this. The laser assembly and its output looks roughly like this. Adding another rotor and laser with some electronics forms a basic base station. For the control logic, this chart shows a simplified timing diagram. The two motors are controlled to have an almost constant angular velocity and always keep a 180-degree phase difference. When each motor passes the starting position, the LED array will flash the sync signal respectively. The format and timing of the optical sync signals can be found in some open source projects. Okay, basically that's how it works. So it should not be too difficult to make one by myself, right? Base stations are mechanical systems, so there will always be some imperfections. This means the lasers could be misaligned, the mirrors could be misaligned, the lenses could be misaligned, and the motors could be misaligned. Ideally, the laser lines would be straight and sweep at a constant angular velocity. However, when the alignments go wrong, they will get distorted, which will cause tracking issues. Valve uses these calibration parameters to compensate for the errors, but the calibration methods are unknown. To make things harder, the level of mechanical precision I can reach is significantly lower than what Valve can do. The frame of the base station is made by die casting, which can achieve excellent accuracy and rigidity. So unless I machine all the components like the Valve prototypes, I can get nowhere near the same build quality. Besides the misalignments, another trouble is that the two motors need to rotate at precisely 60 Hz. It directly determines the accuracy of the angle measurements. I didn't worry too much about that because I thought I could use hard drive spindle motors. So I started prototyping. Initially, I tried to use similar mechanical designs from the base stations, but it went terribly wrong. The laser lines were so distorted that I could see the distortion directly with my eyes. The accuracy of an entry-level FDM printer is what it is. In the end, I had to get more creative. I took some inspiration from low-cost mechanical LiDARs. The solution was to put the entire laser assembly directly on the rotor. This off-the-shelf line laser assembly is relatively accurate. Using it could eliminate most errors caused by the misalignments between the optical components. As a result of this design, I had to put a wireless power module and some electronics on the rotor itself. Ideally, I would use hard drive spindle motors for my base station. But in my case, since I used an off-the-shelf wireless power module, I didn't have enough space to fit all the components on the rotor. So I ended up using stepper motors that have a double-end hollow shaft design for extra space. It was a mistake. I should have designed that wireless power module myself and gone with the hard drive motors. To compensate for the jitter, I put two steel rings on both ends of the stepper motor to increase the moment of inertia. The downside of my design is that with all these components on both ends of the rotor, it's difficult to make it balance. It's still doable, but I made a dumb mistake in assuming the density of PLA is 1 gram per cubic centimeter. As a result, I had to put chunks of steel and many dampers on my base station to stop it from jumping around and oscillating violently. Also, because the stepper motors I chose are not designed to operate at this high speed, I had to put two powerful cooling fans to dissipate the heat. This high-speed footage shows the running base station. Before I could get any reasonable tracking quality, I needed to do some basic calibration. I performed the phase calibration by using a laser pointer to mark the center of a base station and then aligning it to the center of a sensor on the web tracker. After the alignment, I turned off the laser pointer and powered up the base station to get sensor readings. The sensor reading on the X and Y axis should both be 0, so I got the calibration values. After a lot of trial and error, I got everything working. It was pure happiness for me when I finally saw the controller moving with my hand. Thanks to the SteamVR tracking algorithm, it worked surprisingly well. The tracking quality was not as good as the real stuff. You can see there are some jitter and sudden jumps, but it's not too bad. I played some games to get a feel of the tracking quality. I could shoot down some faraway targets in Onward. In Beat Saber, I could play some songs on Expert Plus difficulty without much trouble. Additionally, I tried to verify the absolute accuracy by measuring distances between objects using a pair of HTC Vive base stations as a reference. Due to the lack of further calibration, the error could be up to a few centimeters, depending on the distance and position in the base station field of view. Fortunately, the human perception system can tolerate some discrepancies between visual and proprioceptive feedback. What you see and what you feel doesn't need to match exactly. There is a lot of research on using this phenomenon to redirect or scale hand movements on purpose. I personally don't find this level of error from my base station disturbing. It's hardly noticeable unless I really look for it. I also measured the jitter in base stations. My base station has about 3 times the jitter of the HTC Vive base station. It's just a rough comparison since I didn't measure the velocity variation during each rotation. As a proof of concept, it worked pretty well, although with many problems. Just to name a few, it is incredibly noisy, extremely heavy, and sometimes it doesn't start up correctly due to the violent vibration caused by the unbalanced rotors. I could work on improving it, but at that time I felt I should revisit my earlier failed attempt. So for the next prototype, I abandoned the wirelessly powered laser and went with a spinning mirror, basically the same design as HTC Vive base station. I put up another base station prototype with some easy-to-buy components. To control the motors, I used a proportional integral velocity controller and a proportional phase controller. The control scheme is very simple but worked well. However, due to the motors being sleeve bearing motors and the rotors don't have much moment of inertia, there are tons of jitter in the system. From this video, you can see the controller shakes a lot. Again, I played some games. I didn't feel much difference in Beat Saber, and the experience was not too bad. But in Onward, the aiming became much of a struggle due to the jitter. It was especially bad for dual-handed weapons, as shown in this video. Overall, for a quick test, it worked. Compared to the previous prototype, it's much quieter and vibrates much less. However, the jitter is really bad, and I started to notice the errors in the controller tracking caused by the misalignments and lack of calibration. I looked for calibration methods first. The most obvious method is using the measured value against the ground truth. It's similar to what I did earlier, but to do it with much higher precision. I didn't have the tools to do it, but I still tried. I tried to start with something simple, so I used my previous prototype in order to ignore some of the calibration parameters. My attempt was limited by the accuracy of my setup. It generated very close values to what I got with the laser pointer method. It's definitely not worth the tedious process I went through, so I searched for other methods. Most literature I found is about calibration in a stereo base station configuration, which is not directly helpful to my project, but still provides a lot of useful information. They mentioned strategies like treating the base stations as cameras and applying many camera calibration techniques. With more digging, I eventually found the answer. The idea is, if everything is perfect, then the measured sensor values should be the same as the values calculated from the tracker pose, which is calculated from the measured values first. By trying to minimize the reprojection error from multiple sets of data, the calibration values could be found. Similar to camera lens distortion calibration, it requires a calibration object. However, since we are dealing with photodiodes here, it's challenging to construct such an object, and it could require using expensive instruments to calibrate. Luckily, the headset is already calibrated in the factory and has a long baseline between the sensors, so it is a good option. Enough datasets to cover the entire field of view of the base station could be acquired by either rotating the base station or moving a headset in the room. This idea is not difficult to understand, but the execution was really daunting for me since I had zero experience with computer vision and optimization methods. I could already see problems like geometry of the base station can affect the calibration model. I might try it in the future to fulfill my interest, but for now, I think in the DIY scenario, I still prefer to reduce misalignments through mechanical means. So if I were to make my next base station, I would still choose my earlier approach. One benefit is I don't need to spend time tuning tolerances between components. It's actually quite difficult to get right even with a resin 3D printer, and the result is hardly repeatable. Off-the-shelf laser pointers are simply easier to work with. For the calibration, based on my earlier approach, I would use cross-line lasers and build a calibration plate. I think it's easier to perform than moving a headset across the room to collect data, which is really meant to be done by a robot, and there is no scary mess involved. So the calibration part is finished. Now let's look at the jitter. As you can see, my second prototype has a terrible amount of jitter. The first method to improve it is to increase the rotor's moment of inertia. It's quite effective. Basically, that's how the engineers at Valve got the development kit base stations working. The rotors in the dev kit base stations are probably made of zinc alloy, and it resulted in a solid performance. However, this method is limited by how large and heavy the rotor can be. It also makes the rotor harder to balance and results in higher vibration. Fundamentally, the jitter had something to do with the motor itself, so I tested a lot of motors. The best option is hard drive spindle motors. However, there are a lot of caveats. The first problem is that they are not easy to source. Modern hard drives usually have the motor directly pressed or glued to the chassis. It makes repurposing the motor very difficult or practically infeasible. For the motors that can be salvaged, they come in all kinds of shapes and characteristics. Another problem is I encountered similar bearing behavior as Alan Yates mentioned in his Hackaday talk. I have no idea what's happening here, and I didn't find much information either. I think increasing the rotor's moment of inertia should help greatly, because the motors are designed to carry the platters in the hard drive. Another good option is stepper motors, especially smaller ones like NEMA 11. They have very solid performance and are easy to source. With fine-tuned trinamic stepper drivers, they can operate with relatively low noise at high speed. However, due to the nature of open-loop computation, they have problems like heat and resonance. The rotor must have enough moment of inertia to avoid the resonance band during operation. Here are some options that could work, but I don't recommend them because they are difficult to source. These are the toy options. They have excellent availability and are very cheap. Their performance is rather bad, but if the rotors have enough moment of inertia, they could work. Their performance could be anywhere between the green curve and the red curve. Lastly, motors that have high clogging torque don't work. I first tried a very popular drone motor paired with a drone ESC, and it didn't work. The performance was more than 10 times worse than anything I ever tested. I then tried a driver IC with sinusoidal commutation and tuned the parameters to the best I could. It still didn't work. The performance was just terrible. The clogging torque is usually very high for drone motors. I believe that's the reason for the poor performance. So my conclusion, under a DIY setup, there really is no single best option. I would use hard drive motors if available and stepper motors if not. I originally planned to build a new prototype and a tracker to work with it, but the involvement turned out to be a lot more than expected. So I consider this project finished at this point. You can find the materials I gathered during this project in the repository. The tracker currently doesn't have software to establish tracking or communicate with SteamVR yet. The repo contains the hardware design and a very basic program using the PIO on the Pi Pico to read sensor outputs. As a bonus, I want to briefly talk about two different Lighthouse implementations I came across during this project. Performance-wise, they are worse than SteamVR tracking, but I find their designs interesting. Despite their very different looks, they share many things in common. They both have the ability to measure distance directly. It could make the tracking algorithm easier to design and reduce the sensor count on the headset and controllers. So for example, there are only 6 photodiodes on the E3P headset and 9 on each controller. HTC Vive has 32 on the headset and 24 on the controllers. They all use sleeve barrier motors to reduce cost, and both implement quite heavy motion filtering to smooth the jitter. As a result, both systems suffer from high latency and stutter due to the filter design. In this video, you can see some stutter on the E3P controller. The latency is also quite high, and I had trouble playing Beat Saber even on expert difficulty. The E3P base station had 3 rotors inside. Similar to a stereo camera, the sensor position in 3D space can be calculated from 3 angle measurements and a known geometry of the base station. Here are some pictures of the base station and the controller. The Nolo base station uses ultrasound to measure distance. With knowledge of 2 angles and the distance measurement, the 3D position of the target could be found. Here are some pictures of the disassembled base station. That's it for this video, thanks for watching.